Welcome back, everyone. Today we are strapping in for a highly detailed mission briefing on what is honestly one of the most ambitious planetary exploration efforts of our time. So let's dive right into this. We are looking at China's Tianwen-3 Mars sample return mission. The China National Space Administration recently dropped some massive updates about the international payloads that'll be hitching a ride to the Red Planet, and I am absolutely thrilled to break down exactly what this hardware is designed to do. If you're fascinated by deep space engineering and the hunt for extraterrestrial life, well, this explainer is going to be incredibly exciting.
To wrap our heads around the sheer scale of this mission, we'll quickly look at four main areas. First, the mission timeline and goals. Second, the orbiter instruments. Third, the surface and service payloads. And finally, the selection process.
All right, let's jump right into Section 1, Mission Timeline and Goals.
Before we start tearing down the specific spacecraft components, we really need to establish our temporal anchors here. Space missions of this magnitude usually take years, sometimes literally decades of meticulous planning. But the administration is targeting a remarkably tight timeline for this one. The window for international cooperation opportunities was just announced in April 2025, and by July of that same year, the mission was already being actively showcased at the Planetary Exploration Exhibition at the Shanghai World Expo Museum. But actually, the real heavy hitters to pay attention to are on the right side. We're looking at a targeted launch date of around 2028. That gives engineers a super narrow window to integrate all these complex international payloads. And that rapid-fire launch schedule, it's all in service of the monumental date right at the bottom, 2031. And that 2031 date brings us to the ultimate goal of Tianwen-3. We aren't just taking pictures of Mars this time around. We aren't just driving rovers around in the dust, as cool as that is. The objective is to successfully bring Martian samples all the way back to Earth. Returning material from another planet requires a staggering sequence of events. You've got launching, cruising, orbiting, landing, collecting, ascending back off the Martian surface, docking in orbit, and then surviving that fiery re-entry into Earth's atmosphere. It is, without a doubt, the holy grail of current planetary science.
Moving right along to Section 2, the orbiter instruments. So, to actually pull off a sample return, you need a seriously equipped spacecraft. Starting our zoom-in technique at the top of the vehicle, we find a highly collaborative effort on the orbiter itself. There are three primary payloads riding up top. First up, the Mars PEC spectrometer, led by the Exploration Working Group of the Committee on Space Research. Its primary job is pretty tantalizing, searching for traces of life while mapping out the surface's mineral composition. Next, we have the Mars Molecular Ion Composition Analyzer, spearheaded by the Macau University of Science and Technology. And third, the Laser Heterodan Spectrometer from the Chinese University of Hong Kong, which is officially tasked with detecting the profiled distribution of water isotopes and mapping out the Martian wind fields.
So the absolutely crucial point to understand here is why we're sending things like a molecular ion analyzer. Well, it's all about studying something called atmospheric escape. You see, Mars wasn't always this cold, barren desert we see today. Billions of years ago, it likely had a thick atmosphere and flowing liquid water. Atmospheric escape is the process of a planet literally bleeding its gases out into the void of space. By studying the specific ions that are escaping today, scientists in Macau and all around the world can actually reconstruct the history of the Martian climate. They can figure out exactly how and when Mars lost its atmosphere. It's like piecing together a giant planetary puzzle. All right, let's head further down the spacecraft. Section 3, Surface and Service Payloads. Descending from orbit, we're moving our focus down to the service module and the lander, the hardware that's going to get up close and personal with the Martian terrain. As we break down these lower stages, we see a really clear division of labor and location for our final two cooperative payloads. The service module is going to host the hyperspectral imager, keeping it in a position to broadly scan the terrain from above. Meanwhile, the lander itself is going to physically carry the laser retroreflector array all the way down through the Martian atmosphere, planting it firmly on the alien soil. Let's look at these two instruments a bit closer, shall we?
Okay, so the Mars Surface Object Hyperspectral Imager is being led by the University of Hong Kong. Hyperspectral imaging is incredible technology. It doesn't just snap a regular photo, it captures data across the electromagnetic spectrum for every single pixel in the image. This allows the team to go after three massive goals: detecting the chemical signatures that might indicate past life, hunting down hydrous or water-bearing minerals, and conducting really deep resource surveys of the Martian crust. Basically, it's a high-tech geological treasure map.
And then we have the lander's payload. This is the Laser Retroreflector Array, led by the Frascati National Laboratory of Italy's National Institute for Nuclear Physics. Think of this thing as an interplanetary lighthouse, but one that doesn't even need a power source. A retroreflector simply bounces a laser beam directly back to where it came from. By placing this on the lander, Italy is helping deploy a permanent, incredibly precise reference point right on the Martian surface. Future orbiters can just ping lasers off this array to measure exact distances, which is going to help us map Mars and navigate future missions with pinpoint accuracy.
Which brings us to our final stop, Section 4, the selection process.
We've seen the hardware, but how did these specific instruments actually make the cut? Let's look at the logistics behind the scenes, specifically the rigorous selection process detailed during the 11th China Space Day events. Since the announcement of cooperation opportunities first went out in April 2025, the China National Space Administration received a total of 28 official expressions of interest from various global institutions and space agencies. That's 28 separate proposals from scientists eager to get their hands on pristine Martian dirt. The numbers here brilliantly illustrate the intense, and I mean intense, competition of modern space exploration. Out of those 28 highly detailed proposals, only 5 international and regional cooperation projects were ultimately granted a boarding pass. Space on a spacecraft is arguably the most expensive real estate in the entire solar system. Every single gram of weight is accounted for, meaning 23 hopeful projects had to be left on the drawing board.
So how exactly did the administration filter 28 down to just 5? Well, they leaned on 4 incredibly strict selection principles. First up, high scientific value. The instrument had to offer groundbreaking data, not just repeat old experiments we've already done. Second, strong mission support. It had to actively contribute to the ultimate goal of actually returning a sample. Third, engineering feasibility, like can it physically be built and integrated into the existing spacecraft design in time? And finally, technological maturity. Space is an incredibly unforgiving environment. You definitely don't want an experimental prototype failing halfway to Mars. You need proven, robust technology that is guaranteed to survive the harsh radiation and extreme temperatures of deep space.
We've seen the 2028 timeline. We've explored the instruments from Macau, Hong Kong, Italy, and beyond. We understand the rigorous gauntlet they had to run just to get on the manifest, which leaves us with the ultimate question. When that sample return capsule comes burning through Earth's atmosphere in 2031, will these 5 collaborative instruments have given us the data we need to finally uncover traces of life hidden in the Martian dust? It's a colossal engineering challenge, but the hardware is officially locked in. Keep your eyes on the skies for 2028. Thank you so much for joining me for this explainer, and I'll catch you in the next one.